This conference will now be recorded.
Hello everyone. Cyclic structure of glucose. We ended in this slide. Now, open structure of glucose, how we have all these different evidences, and based on all these evidences, how we have reached the open chain structure of glucose that we have seen in the last class. Now, we will see another structure, which is cyclic structure, that is also possible for glucose. So Fisher identified that the open structure that we have already seen from the based on the evidences, that structure cannot explain some chemical behavior. So that is why the introduction of cyclic structure is there. So what are the chemical reactions that we cannot explain? Unlike simple aldehyde, glucose did not form crystalline bisulfite compound with sodium bisulfite. The reactions I have already shown in the last class. Then glucose does not give shift test. Now there is a test by using shift reagent, where if any free aldehyde group present, that will give positive test. But in this case, we are not getting the test. And the third chemical behavior is the pentaacetate derivative of glucose. Remember, when we treat glucose with acetic anhydride, we get pentaacetate. That means OH group that will be converted to OAC group. OAC group means OCOCH2 group. Now, after converting it to pentaacetate by using anhydride, acetic anhydride, the molecule that you are getting, if you treat that molecule with tolerance reagent or Fehling solution, then reaction is not positive. So the pentaacetate derivative of glucose is not oxidized by tolerance reagent or Fehling test. That means in another way, it is actually trying to say when you do tolerance test or Fehling test, these two reactions are not positive for the pentaacetate derivative of glucose. But if you do these two tests directly with glucose, then it is positive, but not with pentaacetate. So these are some of the behaviors that we cannot explain by the open structure only. So that is why this cyclic structure, this idea is now introduced. So here you can see in the left hand side, this is the open chain structure that we already know. And this carbon is number 1, then 2, 3, 4, 5, and this is 6. Fine. Now, two possibility for the cyclic structure is there, and the difference is only in this position. Now, how we can achieve from open structure, how we can reach towards cyclic structure, that you'll see in the upcoming slides. Right now, just focus on these two cyclic structure. Position number 1. So in this position, the position of, I mean to say, in carbon number 1, arrangement of H and OH group, these two are reversed in these two cases. But if you look at the rest of the part, there is actually no change. Only the change is occurring at this carbon, that is number 1 carbon. And number 1 carbon is now attached to number 5th carbon through oxygen atom. That means this one position and position number 5, now these two will be connected but through oxygen. That means this oxygen may be the oxygen of OH group, and there is also generation of a new OH, because if you look at the open chain structure, you can see how many OHs there. 1, 2, 3, 4, 5. That is total 5 OHs there, right? But now if you look at the right hand side cyclic structure, there are also 5 OHs present, but these 5 OH, they are not the exact 5 OH that you are seeing in the open chain structure. In the open chain structure, the 5 OH groups that are present, position number 2, 3, 4, 5, and 6. Now look at the open cyclic structure. Now the position of 5 OH, again 6 position it is okay, 5 position the OH is no longer present. Then 4 carbon OH is present, just like the open chain. 3 carbon OH present, 2 carbon OH present. And look at number 1 carbon. Now a new OH you are getting, right? So the OH which was previously present with carbon number 5, that was no longer present, and you are getting a new OH which is present at carbon number 1. And this carbon is known as aromatic carbon. Why it is called so? For that, we have to know what is the definition of anomeric carbon or what is the definition of anomers. But until now, this much information we have about the cyclic structure. But how we can get the cyclic structure from open chain, that we will see next. So if you really want to understand how we are getting the cyclic structure from the open chain, you have to know what is acetal and what is hemiacetal. So here you can see the structure of hemiacetal and acetal. The difference in these two structures is only in this position. So in case of acetal, we have OR group, whether it is 3, 4, that is not important, but you have oxygen alkyl group. But in this case, you have OH group. Rest of the part, there is no change. Now this type of hemiacetal and acetal, how we can get? For that, suppose you have started from a keto compound like this, R1, R2, in between there is CO group, and you are treating it with 2 molecules of alcohol, which is R3OH. Then you will get this type of structure by combining these two. But suppose if you want to get hemiacetal, then again the same carbonyl compound. But now only one alcohol. So as if here the alcohol H group, and that is 2 alcohol, 2 hydrogen atom, and these 2 oxygen, they are removed. So I can also write it like this, R3OH, another R3OH, and R1CO, R2. So if you remove water molecule like this, what you will get? You will get oxygen carbon bond. This is a newly generated oxygen carbon bond. So these two are the newly generated bond. Similarly, if you take only one alcohol, then as if this R3OH, it is attacking here. So when it is attacking here, there will be OH and one each atom that will be removed. So this is the difference between the structure of hemiacetal and acetal that we can get starting from any keto compound. It may be aldehyde or it may be ketone. Depends on any of these R1 or R2. If it is hydrogen, it will be aldehyde. In that case, in this position, you can write H. But if it is ketone, both sides there will be some alkyl group. But that most important thing is here. Here when we have taken one alcohol and one carbonyl compound, then you are getting hemiacetal. But if you further use another alcohol, that is now the ratio is 2:1, alcohol 2, carbonyl compound 1. Now you will get acetal. So 2 OR3 group now attached. Now why we are discussing this? Because the same type of mechanism you will also see in case of when we will reach the cyclic structure starting from open structure. So in this case, you have taken carbonyl and alcohol separately, right? But suppose if the carbonyl group and the alcohol, that is OH group, they are present in the same molecule. Now there will be intramolecular reaction. That is within the same molecule if the reaction happens. Now that possibility we will see here. So see, now we have aldehyde group, 1 carbon, and we also have OH. And suppose in between aldehyde and OH, you have 2, 3, 4, 5. That means total 4 carbons are present. So we are trying to make it analogous to the open structure of glucose. So that is why we have taken this type of molecule. So terminal position, you have OH group and CHO group. Now if this oxygen, that is the alcohol, as it is part of the same molecule, if it is attacking here, there will be OH bond formation and this H will be removed. So look at this arrow, the equilibrium, it is mostly towards the cyclic structure. Now this type of cyclic ring, it is known as pyranose. Why it is so? Because the name pyran, that is coming from this molecule. Look at this molecule, this is 6-membered ring with 1 oxygen, there is CC double bond, but just remove the double bond as if we are having same type of structure. So that is why the name is pyranose ring, which is 6-membered, 5 carbon, 1 oxygen in the ring structure. So now we will compare this with alcohol molecule. So the OH group that is present at this carbon. Okay, so if it is attacking the carbon which is present at position number 1, so I'm talking like this, then we can get some formation of cyclic structure, right? And the number of carbons that we will get, that will be, that is, if you consider this is as if 6 oxygen, so it will be 1, 2, 3, 4, 5, 6. So you will get 6-membered ring. So now there are two possibilities. Let me erase this previous discussion. So just remember the mechanism that we have, the mechanism that I'm just erasing. If you follow the same type of mechanism, now this C double bond O, now it will be converted to OH. Now this OH may be towards left hand side or right hand side, and depending on that, you are getting two possibilities. Rest of the part there is no change, and the oxygen which is actually attacking this oxygen is basically this one. I'm just marking this oxygen. So this oxygen, just compare both sides. I mean to say, compare open structure with the cyclic structure. The oxygen is basically the 5 carbon OH group, but that OH is no longer present as OH, as if it is alcohol group. It is attacking the aldehyde group which is at position number 1. Rest of the part there is no change. So depending on whether OH is left hand side or right hand side, you will get two molecules. So one is known as alpha D glucose, another one is beta D glucose. So when it is alpha and you are writing the structure in this way, then OH will be below the plane. I mean, if you consider this 6-membered ring as the plane, this is as the plane, then OH group is below, and in case of beta it is up. Another it is better if you remember it in this way, that in case of alpha, this 6 position primary alcohol group and OH, these two are opposite to each other, but here they are on the same side. So in this way, so that it will be easier for you to remember, right? But two possibilities are there, and both are D-glucose, because the open structure is the structure of D-glucose. So you are just having these two extra terms depending on the orientation of each group. Now this cyclic structure, you can also write it in the form of chair conformation, and how to write it in chair, that also is important to know, because when you get actual question, that question there may be mention of the chair structure, not this type of simple ring structure. So that is why just have some idea about the chair structure also, because we know if you consider simply cyclohexane molecule, it mostly remains in this way. So this is one chair form that is possible. Another chair form is like this. Okay, so that is, it is written one of the two chair forms. So when we have taken alpha D, and this type of cyclic structure representation, that is known as Howard projection. But you can change this Howard projection towards chair conformation. So remember, the open structure is Fisher projection. Then the cyclic structure that we have both sides of this open structure in the box, that is Howard projection. Now we have chosen only the alpha D, and if you convert it towards the chair conformation, it will be something like this. Okay, so here CH2H group at 5 position and OH group at 1 position, they are opposite to each other. So see, now this is up and this is below. Fine, and we know when we consider chair conformation, there are actually axial bond and equatorial bond. Okay, so axial bonds are like this. I'm doing it with black color so that you can differentiate the axial bond and equatorial bond. And when it is equatorial, now it will be this one. Fine. So the blue bonds, they are equatorial bond. So here sometimes equatorial bond, not necessarily it has to be down, it may be down also, it may be up also. So see, this equatorial bond, it is down, but this equatorial bond, it is up, which is basically depends on the orientation. But important thing is, at 1 and 2 position, the two OH group, they are on the same side. That means they are Cs. Now, when you move from normal ring structure to chair type of ring structure, then how to represent the Cs? The Cs will be either, that is axial equatorial or equatorial axial. But when it is trans, so this is for Cs, but when it is trans, it will be either axial or equatorial. Remember this. So see here, one is axial, another one is equatorial. Then focus on 2 and 3 OH. These two are opposite to each other. That means they are trans. So that is why at 2 and 3 position, both are equatorial, isn't it? This is axial. Then focus on position number 3 and 4. The two OH group again trans. So at position 3 and 4, these two are also equatorial according to trans, because axial normally it is highly energy requiring. So mostly whenever you will have trans configuration, it is mostly EE, I mean equatorial. Fine. Then position number 4 and 5, you have OH group and CH2OH group. So they are anti to each other. So 4 and 5, you can see this 5 bond is also equatorial. So in this way you can understand when we are moving from hard projection to chair conformation, how the bonds are changed. Okay. So some more clarity if we want to get, this is the open structure. Here the lone pair that is present over the OH group of carbon number 5, that is attacking the carbonyl carbon. Now these double bonds, it will no longer be present, there will be single bond. And this type of cyclic structure, don't think this is CH2, this is actually like, it's written in this way. So C is directly carbon number 1, that is directly attached to oxygen. Fine. So see, when it is alpha D-glucose or D-glucopyranose, both names are fine. In that case, this OH, their position, there are no change. But when it is alpha, now this OH, it is on the left hand side. And when it is beta, now it is in the, sorry, this is right hand side, this is left hand side. Okay. And when we convert it, so these two positions we are focusing with red colored box, because only difference is in this position. Rest of the structure, if you see carefully, there is no change. So when we convert it to cyclic structure, now OH group, it is in the left hand side, and this is the position, it is up. And when it is right hand side, now it is down. Again, I am saying there is no other change. Now this type of carbon, which is carbon number 1, we have already seen that it is called anomeric carbon. Now anomer, what is anomer? Though the definition we will also see after in another slide, but anomer is one type of isomerism. If you look at these two cyclic structure carefully, they are actually same, that is they are isomer to each other because same number of carbon, hydrogen, oxygen present. So only difference in these two isomer is the position carbon number 1, that is the position of H and OH. So when you have, I mean, several chiral center, here we have so many chiral center, all these centers are chiral. But among, suppose there are total, just I am saying arbitrarily, total 5 chiral center. Out of these 5 chiral center, if only one chiral center, there is difference. So rest of the chiral center, there is no change. Out of these 5, if only at one center, there is difference in, that is if one is R, another one will be S. So only in one carbon center, there is some change, and this type of isomerism is known as anomers. They are anomer to each other. And the carbon which is responsible for this isomerism, that carbon is known as anomeric carbon. We have a question just related to all this discussion. For the below given cyclic hemiacetal, below means this structure, this is actually X. This is cyclic hemiacetal. Why we are calling it hemiacetal? Remember, hemiacetal general structure is the carbon will contain OH, it will also contain some OR group, But if this OR is part of the same molecule, now I should write it in this way. Suppose it is part of the same molecule, then it will be something like this. So this OH for the hemiacetal, this is actually this one, and then we have oxygen which is connected to some other part of the same molecule. Fine. Now not necessarily the structure that is given that has to be glucose or anything that you know, but remember, if we look at the previous structure, just compare. Here OH group that I have marked with blue color, that OH, it is in the left, right? That means if it is in the left, you can consider as if the structure will be, just look at the carbon number 1 of beta D glucose. It is up, right? Now when it is up, that you can find in which structure? Suppose this is 1, 2, 3, 4, 5, 6. So this is the carbon number 1. And oxygen, that is OH group, that is up because it is in the left hand side. That is present only in option A and option B. Option B as well as B and D. So C you can cancel. Next thing is carbon number 1 and 2. The two OH group, they are on the same side. But C already we have cancelled. But in option A, these two OH, they are on the opposite side. Then option B, same side. Option D also same side. Right? So this is also cancelled. Now you are stuck between B and D. Now, if you further see 2 and 3, these two OH, they are anti to each other. Now that is also same in both option B and option D. Then carbon number 3 and 4, two OH, they are anti to each other. See here 3 and 4, they are anti to each other. But in option B, they are on the same side. So based on all this, what conclusion we can reach? Which option is correct? Obviously it is option D. Okay. So in this way we can choose the correct option. So here we have basically found the correct pyranose structure. Some more information for the cyclic structure of glucose. Basically now we know what is alpha D glucose, what is beta D glucose, I mean two anomers, and what are some extra evidence that there are actually two cyclic structure. We know there is one open structure, and when you move from open to cyclic there are two structure. But what are the proofs? See, we have some information here. Glucose is found to crystallize in two different forms. That means two different types of isomers are there. And the solid that you are getting after crystallization, the alpha form is having melting point 419, and beta, it is different, 423. This also result in the conversion of achiral aldehyde carbon into achiral 1. Remember, carbon number 1, initially that was aldehyde. Just remember the open structure. It is simply aldehyde, right? It is not chiral center. But once it is attacked by the 5-hydroxy group, now there is generation of chiral center. So that is, it is mentioned achiral aldehyde carbon. Now it is converted to chiral 1, and as a result, there will be two possibilities. Either it will be R configuration or S configuration. So that is why we are getting two isomer, and these two are related to each other as anomer. And these two anomeric forms are beta glucose and alpha glucose. And their specific rotation. Now, details of specific rotation, even if you don't know, it is fine. But remember, this term we use only for chiral compounds, because when it is chiral compound, they can rotate the plane polarized light either clockwise or anti-clockwise, and the degree of that rotation, it has some value. For any particular compound, it is having a fixed value. That is, it is exclusive for each molecule. And when there is positive, this is actually plus 112. This is also plus. Plus means it is rotating clockwise. If there is negative sign, that means it is rotating anti-clockwise. So one is 112 degree, another one is 18.7 degree. That is for alpha, this is for beta, respectively. Now another new term we have to know here, which is known as mutarotation. Okay, and that is, if you want to understand it, this information you have to focus. So what you are seeing here, specific rotation for alpha 112 degree, positive value. For beta, it is 18.7, hugely different, right? Now suppose you have taken any pure form of sugar, I mean carbohydrate, not necessarily that is, it is actually observed for other carbohydrate, but in this case we will take glucose. So when a pure form of any of these sugars is dissolved in water, any of these sugars means, sorry, I mean to say any of these alpha or beta. Suppose you have taken alpha one time, another time you have taken beta. So it doesn't matter whether you have started from alpha or beta. In one case you have started with pure alpha form, another case you have started with pure beta form. But whatever is the case, when you dissolve it in water, what happens? Now there is slow interconversion of these two forms. Alpha D glucose will be gradually converted to beta, and beta will be gradually converted to alpha. But that is possible only via the open chain form. Alpha D directly cannot be converted to beta. It has to go through the open chain form. Then only it is possible. And ultimately, an equilibrium is reached, and which gives a constant specific rotation. Now look at the value. It is not 112, it is not 18.7, it is something in between. So the opening and closing of these two structures, it will continue until what? Until it reaches this value. So this is the equilibrium value for specific rotation. Okay, so the opening and closing repeats continuously in an ongoing interconversion between these two aromatic forms, and this process is known as mutarotation. So when you have reached the mutarotation equilibrium, if you look at the quantity percentage of these three forms, so the open chain, it is very less, even lesser than 0.01% out of 100, and the alpha form, that is present 36%, that is the equilibrium composition I'm talking about, and the beta D, that is present, and that is, it is quite double amount, not exactly double, but this form is more, I mean, if you take the ratio, this form is present in higher amount. So it doesn't matter whether you have started from pure alpha, then also you will reach this composition. You have to give some time obviously for equilibrium to reach, and if you start from pure beta, then also you will reach the same composition. Okay, so this process is known as mutarotation, that is conversion of the two anomeric forms, and this is, that is, it is actually occurring, that how we can understand, that is clear from the specific rotation value, because as the final value is 53, so this much information is enough to reach the conclusion that obviously pure alpha form is no longer present, even if you have started with pure alpha, but now it is not present, and also pure beta is not present. So something in between, I mean some form of alpha, some form of beta is present. So that is why we have this type of percentage. And the open chain, mostly glucose remains in cyclic form, so this percentage is very low. If actually if you add these two percentage, you will get 100, right? 6 and 4 0, and then 100 if you just add these two values. So that means open chain structure is very less percentage. So after glucose, finishing glucose, which is very important monosaccharide, another monosaccharide we have to know, which is fructose. So this is another commonly known monosaccharide having the same molecular formula just like glucose. Then what is the difference? The difference is, unlike glucose, now it is ketohexose. Ketohexose means in glucose, what you have seen, aldehyde group is present. The left hand side, right hand side picture, green color. But now there will be C double bond O. And C double bond O cannot remain in the terminal position. Both sides there must be some alkyl group. So that is why now its position is here. So if you are considering this is carbon 1, in case of glucose, carbon number 1 is carbonyl carbon. But when it is fructose, as it is keto, you cannot have it in the terminal position. It has to be in between. So now it is at 2 position. So it is ketohexose. Hexose because it is 6 carbon. Just same thing as you know for glucose. So for glucose it is aldohexose. Now it is ketohexose. And glucose is naturally dextrorotatory, but now it is levorotatory. That is another difference. Its present is very abundant, mostly in fruits, and it is also known as fruit sugar. So if you compare these two structures, you will see in the boxed region there is actually no change. Same OH position, right? Only difference is at 1 and 2 carbon. Okay, so try to understand the difference. Otherwise, molecular formula same. Both are having same number of carbon, but this is keto, that is the molecule that we are going to discuss now, and glucose, there is aldehyde. So we are trying to understand how we can make it. So from sucrose, fructose is obtained. This is the most that is common method from sucrose, because sucrose is disaccharide. Remember disaccharide definition, when it is actually one type of oligosaccharide. After hydrolysis, the definition of oligosaccharide says you get 2 to 9 monosaccharide. So in this case, you are getting 2 monosaccharide, that is hydrolysis of sucrose you are doing. You are getting 2 monosaccharide, and these 2 monosaccharide, it means that this is disaccharide. I mean sucrose is disaccharide. So here we are using H2SO4 water, but when it actually happens in vivo, I mean inside the body, there is an enzyme, that is biological catalyst enzyme, which is responsible for this process, which is invertase. But otherwise, if you simply that is in vitro, if you consider, in vitro means outside the body, then what happens, if you simply take acid medium water, simple hydrolysis, then also you get these two. So one is glucose, that you already know, and this molecule we are now going to discuss. Molecular formula is same. So if you write it in this way, you will not be able to understand which one glucose, which one fructose. If you write it in Fisher, then only it will be clear. Another method is also there, which is large scale. Commercially, if you want to make it, then prepare commercially by hydrolysis of insulin. Insulin is actually polysaccharide, that means complex structure. So C6H12O5 whole N number of water, acid medium, we are getting N number of monosaccharide, which is fructose in this case. And after preparation of fructose, let's see the structure of fructose. Remember, when we have established the structure of glucose, we have seen some evidences. So same thing also we are going to do. So some methods you will find that it is just same as glucose. That methods we will not discuss in detail, because that you have already seen in case of glucose. Only in some cases it will be something new, and that will be discussed in detail. So fructose, it is the sweetest of all known sugar, readily soluble in butter. Look at the specific rotation value now, minus 133 degree. So it is now negative, it is levorotatory. And when it undergoes mutarotation, just like glucose, what you have seen, alpha form 112, beta form 18.7, after equilibrium, that is mutarotation, it is having value 53. So just like that, from specific rotation minus 133, now it is changing to minus 92 degree when it is at mutarotation equilibrium. Similar to glucose, the structure of fructose we can deduce from the following facts, I mean evidence. Remember the first evidence what we have done in case of glucose, elemental analysis. Elemental analysis, molecular determination, it proves this should be the molecular formula. So this is very basic initial information, but gradually we will see details, evidences. If you use HI and red phosphorus, so these two are the reducing agent combination that we have already seen in case of glucose. And then also we have obtained N-hexane major product, 2-iodohexane minor product. So here also the same thing. And obviously the conclusion is also same. What conclusion? Now you have 6 carbon chain in linear form, straight chain. Evidence number 3, that is also same as glucose. There we have seen how it is reacting with hydroxylamine NH2OH, hydrocyanic acid HCN, and it shows the presence of carbonyl group, because only with carbonyl group these molecules can react. Fine. So up to this, it is just like glucose. Number 4, evidence number 4, fructose reacts with acetic anhydride in the presence of pyridine. Pyridine is always used in this reaction because to consume the byproduct, which is acetic acid. Here also we get pentaacetate. So again it proves there must be 5 hydroxyl groups. Otherwise, how we can get pentaacetate? So in presence of acetic anhydride, that is Ac2O, any OH group that is converted to OCOCH3. Or sometimes you can also write it as OAC because AC means COCH3. So if there are 5 OCOCH3s, obviously it proves there must be 5 OH groups. Evidence number 5. Fructose is not oxidized by bromine water. Now you are seeing something which you have not seen in case of glucose. Because in glucose you have seen oxidation is possible with bromine water, which is not very strong oxidizing agent, but still oxidation is possible. But in this case it is not possible. So now you will draw some conclusion which is unlike that of glucose. So this rules out the possibility of absence of aldehyde groups. So as it is rules out, yes. So possibility of, not absence, possibility of an aldehyde group. That is not possible because if aldehyde group is present, that will easily be converted to CO2H group. But we know in case of fructose, though we are trying to establish the structure, but we already know the fact that here we have C double bond O, not CHO. So C double bond O, that is not so easy to oxidize. That is, CHO is easy to oxidize to CO2H. Whether you use weak oxidizing agent or strong, it will always be converted to CO2H. But when it is fructose, there is actually no aldehyde. Now you have keto group, C double bond. So it proves there must be, that is, at least one thing is clear, there is no CHO group present. So this rules out the possibility of aldehyde group. Next evidence, if we are using sodium amalgam. Now this reaction we have not done in case of glucose. This is also something new. So you are using the reducing agent sodium amalgam, which is NaHG, and water. What it produces? Fructose produces, in presence of NaHG and water, sorbitol and mannitol. So these two are some monosaccharide. Now these two molecules, they are related to each other as epimer. What is epimer? That we will see. It is epimer at the second carbon. So this new asymmetric carbon, that is the second carbon. It proves that the second carbon is actually the carbonyl carbon. So this is fructose, carbon number 1, carbon number 2, 3, 4, and so on. In presence of sodium amalgam, look at position number 2. So this position, there is now generation of CHOH starting from C double bond. So you are getting alcohol, secondary alcohol starting from keto. So obviously it is reduction. That is why reduction sign is there. Rest of the part, there is no change. So in these two molecules, how they are different to each other? They are different to each other only at carbon number 2. Rest of the part, look carefully, there is no change. Isn't it? So see, this is the definition of epimer. You have different configuration only at one position, because otherwise there are total 4 chiral center, but out of this 4 chiral center, only one position is different in the position arrangement of H and H. Otherwise there is no difference, and this is known as epimer. Now try to recall anomer, alpha form, beta form. That is also the same type of definition, isn't it? Only at one carbon there is difference in arrangement of the groups. So what is the difference? Basically anomer, it is a type of epimer. Epimer is the more broader sense you can say, and anomer mostly we use in case of cyclic structure of glucose. So it is a special case of epimer. But definition is same. That is, out of different chiral center between two molecules, only one center there will be difference. Other centers will remain same configuration. So what is epimer or anomer? An epimer is one of the two stereoisomers that differ in the configuration only at one stereo center. And anomer is basically a type of epimer. It is one of the two stereoisomers, but difference is now it is in cyclic. So it is a special case. But basic definition is same. That differs only in its configuration only at one position, which is the hemiacetal position. Or it may be sometimes acetal, though that example you have not seen, but You will also see in some other topic. Remember, the carbon where hemiacetal is formed or acetal is formed, if at that carbon you are having two different configuration, then you can call these two isomer as anomer. So this is a special case of epimer. Fine. So this is evidence 6. Evidence 7. Now we will do again oxidation, but we will use strong oxidizing agent. So when you are using strong oxidizing agent like nitric acid, now oxidation is possible, because in the previous case when you have used bromine water, which is mild, not strong, evidence number 5 I am talking about, in that case you have seen there is no reaction, which proves absence of aldehyde. But now you are using strong oxidizing agent, reaction is occurring, and here actually CC bond cleavage is taking place. So here we have total 6 carbon before oxidation. After oxidation it is 2 carbon and 4 carbon. That means the breaking point is somewhere here, right? So from this part, CH2H and C double bond O, that is now converted to CO2H. This molecule is known as glycolic acid, and the other part containing 4 carbon. Now the two terminal position, this is now one terminal, this is another terminal. These two terminal that will be converted to CO2H, and this molecule is known as tartaric acid. So when we use strong oxidizing agent, now there will be oxidation, but obviously it will involve CC bond cleavage, because without cleavage you cannot make any change at this position of C double bond O. You have to break it, then only you can get CO2H. Otherwise how you will get CO2H? You have to break CC bond. Fine. So now we are getting glycolic acid, tartaric acid, which contains smaller number of carbon atoms because it involves CC bond cleavage. But it also proves that a keto group is present at position number 2. So cleavage is basically taking place in between 2 and 3 carbon. And it not only proves that keto group is present at C2, it also proves that 1 degree alcohol groups are present at 1 and 6 position. So 1 and 6 position is basically these two position, right? And as that is this type of compound that you are getting, it also shows that 1 degree alcohol group present at C1 and C6, right? So 1 degree alcohol that is still present here, but in this case this 6 carbon, now 6 carbon which is 1 degree alcohol, this is also 1 degree alcohol. 1 degree alcohol, it is still intact here, but in the second case this 1 degree alcohol that is converted to CO2. So from all these 7 evidences, this is the structure of fructose that we have arrived. So here carbon number 1, 3, 4, 5, 6, it is just like glucose. Only difference is at position number 2, where in case of glucose you have C attached to H and OH, but now it is C double bond O. Sorry, it is also different in position 1, because when it is glucose it is actually CHO4, not CH2H. So basically in fructose you have 2 1 degree alcohol, 1 position, 6 position also 1 degree. But in case of glucose you have only primary alcohol at position number 6, not any other. Rest of the weight they are secondary in nature. So now as we know the open structure of fructose, and remember in case of glucose, after discussion of open structure, next we have moved to how we can reach the cyclic structure from the open structure. So same thing we'll also do here. Cyclic structure of fructose, just like glucose, here also cyclic structure will be there, but unlike glucose, now it will be 5-membered ring. What you have seen in case of glucose, it is 6-membered cyclic structure, pyranose, but now it will be furanose, and the term is derived from furan, because the structure furan is this one. Remember, when it is pyranose, it is 6-membered ring, out of which 5 carbon 1 oxygen, but now it is 4 carbon 1 oxygen. That is the difference between furan ring and pyran ring. So from pyran you get the terminology pyranose, from furan you get the terminology furanose. So now we will get cyclic structure, but it will be 5-membered, That is why it is furanose form. When fructose is a component of saccharide, as in sucrose, it mainly remains in furanose form. Remember, sucrose we have used during the preparation method of fructose, right? Because sucrose is disaccharide. So when you do hydrolysis with sucrose, you get one monosaccharide glucose, another monosaccharide is fructose. But it is, the last point is saying, suppose it is remaining in the component form, not free fructose. It is in the component form in the disaccharide sucrose, from which you can get fructose after hydrolysis. But suppose if it is in the combined form, it remains in this furanose form. That means 5-member ring form. Okay. So this is one structure possible. And see, if you compare this structure, carbon number 5, this OH. Now if it attacks here, then how many? That is 1, 2, 3, 4 oxygen. That means 5-member ring will be there. And position number 1, this 1 degree alcohol. Position 6, another 1 degree alcohol. These two will remain same. And at 5 position, the OH that is present, that will attack the 2 carbon, which is carbonyl carbon, and you will get a new OH. So this must be the position of 2, or you can say aromatic carbon. This must be the position 5. This must be 4. This must be 3. And this is 6. This is 1. Okay. Now it is alpha. Another form that is possible, which is beta. Same thing. That is positions are, this is 2. This is newly generated OH. I am not giving any number here, but it is 5-member, right? It is 1. Sorry, it is 2. So I am not giving number to the ring. I am just comparing the numbers with the numbers that is already present in the open. So if I am writing 5 here, it is actually this carbon. That is the carbon in the 5 carbon in the open chain. Okay. So beta form and alpha form. So these two are anomer to each other, but it is 5-member. That is important difference with glucose. Now chemical reactions of glucose and fructose, we will see, that is together simultaneously. We will see if we take any particular reaction, both the reactions, that is both the compounds, will be discussed simultaneously. That is, if there is any particular reaction, we will try to see how it happens in case of glucose and how it happens in case of fructose. Okay. So that is why the heading is common, that is both glucose and fructose. Now glucose and fructose, these two structure, if you consider, there are actually 3 types of groups. Obviously you can think that why 3? It must be 1, 2, because you have simply OH group or carbonyl group. Maybe the carbonyl is for aldehyde type or keto type, but one carbonyl, one OH. But actually there are 2 types of OH. One is glycosidic OH, another OH alcoholic OH. So alcoholic OH, that is simple alcohol OH. But glycosidic OH is that OH which is generated, newly generated, when you move from open to cyclic structure. At that moment it is generated. So this is actually the aromatic carbon newly generated OH, and that is known as glycosidic OH. General chemical reactions of glucose and also fructose is because of these active groups present in it. So here we have written aldehyde CHO. So I am giving, or it may be keto group also, if you also consider fructose. Suppose both are there. So it is either aldehyde or keto, but other 2 active groups, they are basically 2 types of OH. Okay. So the first reaction is glucoside formation. Glucose reacts with methanol. Not necessarily it has to be methanol, you can take any other alcohol, in presence of acid HCl and you get alpha and beta glucoside. Now it is because of the reaction of alcohol with glucoside OH group of glucose. So just remember the cyclic structure of glucose, where you have the glycosidic OH, I mean the aromatic carbon OH, newly generated OH. That OH will react with methanol. So the compound that you will get from beta D glucose, that will be beta D methyl glucoside, and from alpha it is alpha D beta glucose. And the same way fructose can also give you molecule, but now the name is different. Here we are calling it glucoside, it will be fructoside. So see, we have taken the cyclic structure. Though the cyclic structure, it is not written in Howard projection, it is written in Fisher, but it is actually the same thing, right? So the alpha D glucose, where this OH, it is towards right hand side. You can also draw the Howard position, it is actually same. But remember this carbon, which is carbon number 1, right? Sorry, until now I have said for carbon number 5, the newly generated OH. It is actually not carbon number 5, it's carbon number 1. Carbon number 5 is this one. Okay, it is connected to carbon number 1 now after cyclic structure formation. But this is the newly generated OH, I mean glycosidic OH. This OH will only react with methyl alcohol. It is 1:1 reaction. Rest of the OH, there is no change, and we are getting this molecule. And you can also convert it to Howard, which is basically this one. So see, now the OMe group, which is right hand side in case of alpha. So when you write simply alpha, you write here OH, right? But now you have written OCH3. If it is any other alcohol, suppose ethyl alcohol, it will be OET or O-propyl. But important thing is only this OH is taking part in reaction. 6 5 carbon, 1 carbon. Okay, so you can draw it in this way, that is cyclic structure, just like as if you have drawn it in Fisher position, or you can draw it in Howard, whatever you are comfortable with. But remember, this reaction is also possible for fructose, same type of reaction. It is better if you practice it. That is the same, that is just follow the same reaction, but you have to write it for fructose. So here attack will be, that is not attack, I mean to say, in case of fructose also, if you consider the previous structure, these two OH which is in pink color, only this OH that will be converted to OMe group or OET, depending on what alcohol you have taken. So same type of reaction you can also draw for fructose. Oxidation. Glucose when treated with bromine water, that is one type of oxidizing agent. Or if you use tolerance reagent, which is silver nitrate in ammoniacal solution, basic medium, then you can use Fehling's reagent, which is basically copper 2+ in aqueous sodium tartrate solution, or Benedict reagent, that is also Cu2+, but medium is to some extent different. But in both cases it is Cu2+. So you can take bromine water, Tollens reagent, Fehling's reagent, Benedict's reagent. All these are basically oxidizing agent. So in all cases, why we have taken all these reagent together? Because product is same. So whatever oxidizing agent you take, you will always end up with gluconic acid. And what is gluconic acid? Only the aldehyde group is oxidized to carboxylic acid. So when it is Tollens reagent, Ag plus will be converted to, I mean reduced to Ag, metallic silver. In case of bromine, bromine will be converted to HBr, that is from Br to now it is Br minus. When it is copper 2+ in case of Fehling and Benedict, it will be reduced to copper plus. So in all cases, this species, oxidizing species, that itself reduced. So the product is D-gluconic acid. You can take any of these oxidizing agent, and these are the fate of the reagents. Bromine, when it is in bromine form, it is red color, but when it is in Br minus form, it is colorless. Then silver plus will be converted to metallic silver, which is basically the silver mirror. Copper 2+ will be converted to Cu plus. Cu2O is nothing but Cu plus. 2 Cu plus, 2 negative charge over oxygen. balanced neutral molecule. It is red solid. So whatever is the reagent you have taken, you will always end up with this, where the change is only in this part. Rest of the part, no change. But if you take stronger oxidizing agent, suppose you have taken nitric acid, now what will happen? Now there will be something different. Both aldehyde as well as the primary alcohol, 1 degree alcohol, I'm talking about the alcohol at 6 position. Now both will be oxidized because now your oxidizing agent is strong. And the name is different, glucaric acid, also known as saccharic acid. So both positions are now changed, unlike mild oxidizing agent. Rest of the part, there is no change. Okay. We can also do reduction. We have to use some reducing agent, and reducing agent you can take sodium amalgam or you can take hydrogen under high pressure, but catalyst is required. Now this reduction, it is because of aldehyde or ketone group, depending on you have taken fructose or glucose. And obviously in both cases, whether it is aldehyde or ketone, you will get alcohol because now you are reducing it. When aldehyde, it will be primary alcohol. When it is ketone, it will be secondary alcohol. But details as we cannot discuss today because we are at the end of the session. So that is why we are ending at oxidation. We'll also see some more reactions for glucose and fructose in the next class. Thank you for listening.